everyone. Welcome you all to the sixth lecture of module 3, in which we are going to discuss random walk model. Now, in random walks, one is allowed to move with either value +1 or -1 with probabilities P and Q, where probability of moving with +1 is P and probability with moving with -1 is Q, and this probability P is considered as probability of the success. Then Q will be probability of the failure, and this Q will be 1 minus P. It is not P minus 1 but 1 minus P. Now here we assume that the outcome of this random experiment will either result into success or result into failure. So if the outcome result into success, the random value assigned will be +1. If the outcome results into failure, the random value assigned will be -1. And this random variable is actually moved in a particular direction with +1 whenever success occur, and it will move in -1 whenever failure will occur. So since it is depending upon the probability of success and failure, we can easily model or understand it by using Bernoulli's trial. So let us consider the Bernoulli's trial x1, x2, xn with probability of success equals to P in each trial. So at kth time or after kth trial, let us say we represent the random variable by xk. So xk will become equals to +1 if kth trial result into success. Xk will become equals to -1 if kth trial result in failure. So random walk model is actually used to find out the accumulated positive or negative excess at nth trial by using this Bernoulli trial. So to get that accumulated positive or negative, let us say we consider the sum Sn, where Sn is defined as x1 plus x2 plus up to xn with the starting point s0 equals to 0. What it means, let us say we have initially the particle is at 0th location. After the first trial, that is at this point x1, if this first trial results into success, particle will move to +1 position. Whereas if first trial results into loss, particle will move into -1 direction. So in this sense, x1 will represent a particular value +1 or -1. +1 in the case first trial result into success, -1 in the case first trial result into failure. So x1 will be equals to either +1 or -1 depending what is the outcome of the trial, failure or success. Similarly, x2 will also represent the value +1 or -1 depending the second trial is a success or a failure. So correspondingly, the last trial xn in this series will also represent either +1 value or -1 depending nth trial is results into success or failure. So if we add up all these values of +1 and -1 depending the actual cases of success and failure, then we call this as sum Sn. So if a particle is allowed to move with +1 or -1, let us say initially it has this point 0. If first trial result into success, it will move to +1. If second trial result into success, it will move further with +1, that is at +2. But if the third trial result into failure, then it will move back to plus 1, that because it has to move with minus 1. So depending upon how many number of successes and how many number of failures that particular experiment outcome will be, at the nth trial the accumulated positive or negative will be represented by Sn. Accumulated means we are just adding up the plus 1 or minus 1 after completion of each trial. So because of this, after nth trial, what may be its accumulated value? Positive, if the trial results into success, it will be positive. If the trial result into failure, it will be negative. So we can say that the sum Sn represents the accumulated value of these random walks. So in a random walk model, actually the particle takes a unit step up or down. Means just like this one, if we have considered here horizontal axis, but if we consider here it as a vertical axis, and initially it is at 0, and particle will take plus 1 depending if the event is success, with minus 1 depending if the event or trial is failure. So this is called as random walk model, where particle takes a unit step up in the case of successful trials, or unit step down in the case of failure trial. So Sn definitely will represent the position of the particle after nth step. So since here the particle will move upside or downside depending upon success or failure of the trial, or we can say particle is walking in upper side or downside depending upon success or failure of the trials. So this particular phenomena will be called as random walk model. And the occurrence of success and failure, the occurrence of success is associated with the probability P, the occurrence of failure is associated with the probability Q. So we can say that if the values of P is equals to Q, that it both will equals to half, then the random walk we will get will be symmetric. Otherwise, when P not equals to Q, random walk we will get as asymmetric. So in this lecture, first we are going to discuss where it is going to apply, then some of the mathematical concept behind this, and then we will discuss one particular example where it is actually used. So random walk model is used to study, first example is motion of gas molecule in diffusion process. You have already know what is the diffusion process. Diffusion process, when particles start moving from higher concentration to lower concentration, then the motion of those particles from higher concentration to lower concentration is actually used to model by using random walk model. Similarly, thermal noise phenomena and stock value variation of a particular stock is also used to model by using random walk model. So these are just few examples, but random walk model can also be utilized in a very long list of application. So we can say that in random walk we model, or we try to study the long time behavior of a prolonged series of individual operation, because at each trial we study whether the trial results into success or failure, then we study this phenomena for a long time, and that long time results into a series of individual operations. So we can say that random walk is actually the study of long time behavior of a series of individual operations. Now in this discussion, in this lecture, actually we are going to discuss these 3 points. There are many other points, but in your course we are going to discuss only these 3 points. Actually we are going to calculate what will be returned to 0 event, and that return to zero event we are going to determine what will be first return to zero case, what will be rth return to zero case, and what will be waiting time for the first return to zero case. How it actually derived, because let us say initially the particle is at location 0. Now when first trial happens, so depending upon the failure or success of that trial, particle will move upside or downside. Then after nth time the particle will somewhere either in positive side or somewhere in downward negative side, depending how many number of failures and how many number of successes it encounters. So at the or after the nth trial, where the particle is actually located, that will be decided by failure or success of the trials. So in first return to zero, we are going to calculate after initial position of the particle is at the zero, after how many number of trials it will again reaches this zero location. Similarly, rth return to zero and waiting time for the first return to zero we also going to calculate. So let us consider first how we actually model a random walk, and then we try to calculate these three cases. Since we have already discussed that random walk is nothing but a Bernoulli trial, or it can be modeled by using a Bernoulli trial. So let us say we represent probability PNR, which is the probability of event Sn equals to R, and it actually represent that what is the probability that particle is at point R. The particle is at point R after nth trial, or we can also say that the probability Sn equals to R or PNR actually represent the probability of the event at stage n and the particle is at point R. So it actually means you have performed the experiment n number of times, that's you are getting the, or you are reaching the stage n, and after performance of nth time the same experiment, what will be the location of the particle. So if the location of the particle is at r may be either some positive integer or some negative integer, then we call that probability as p and r. So we already know that for Bernoulli trial, this probability is actually given by this expression nk p to the power k q to the power n minus k, where it is assumed that out of n trials, k trials results into success. It automatically means n minus k trial will result into failures. P is the probability of success, so probability of success to the power number of time of success multiplied by q, which is probability of failure, that is 1 minus p. So probability of failure times number of times of failure. So this is the Bernoulli trial expression. So we are going to use this expression to actually analyze the probability of random walks for different scenario. Now here k represent number of success in n trial, and it automatically means n minus k will represent number of failures in n trial, and we have just assumed that after stage n the particle is at point r. It means r should equals to number of success minus number of failure. If number of success is greater than number of failure, the value of r will be some positive integer. If the number of success is less than number of failure, then the value of r will be some negative number. And if you solve it, you will get the value of k equals to n plus r by 2. So just if we just substitute the value of k at here, you will get p and r equals to n plus r by 2, p to the power k q to the power n minus k. You can also substitute the values of k here, but we are not substituting here, just to show the expression in a simpler manner. Now this is a, or this in this combinatorial n and n plus r by 2 both must be integer. Now in order to n plus r by 2 become an integer, what we require that either both n and r will be odd simultaneously or both will be even simultaneously. Only then you will get n plus r by 2 as a integer. So if n is odd, it automatically means r will also be odd. If n is even, r will also be even. Now let us consider how we can determine the return to zero scenario. Now return to zero, it means after nth trial, if Sn becomes equals to 0, that is r equals to 0, we can call that is the case of return to 0. So if the accumulated number of success and failure are equal, only then you will get Sn equals to 0, because Sn is summation of all the successes and failure. For successes it is equals or it is a summation of plus ones. For failures it is summation of minus one. So after nth stage or nth trial, if we want Sn equals to 0, it automatically means number of successes should equals to number of failure. So if we consider n equals to 10, 5 times failure will occur, 5 times success will occur. For success you will get plus 5, for failure you will get minus 5, and if you add up you will get Sn equals to 0. So in this particular scenario we will confirm that r equals to 0, means after nth trial or 10th trial the particle will remain or remains back at origin, that is r equals to 0. And if we consider the number of success equals to number of failure out of total n number of trial, where k is the number of successes, it automatically means the total number of trial equals to twice into number of successes. So n equals to 2k. So if we want to determine the probability of return at 2nth trial, so probability of return at 2nth trial means we actually want to calculate probability S to n, because we are calculating after 2nth trial, and probability of S to n will return to 0 means the value of r equals to 0. So we actually want to calculate what is the probability of the event S to n equals to 0. So it will be equals to, in place of n you should replace it with 2n, because you are calculating 2n number of total trial. Number of success out of total 2n will be n, because n equals to 2k. So 2n n, p and q both multiplied to the power n, because p to the power k, that is p to the power n, q to the power n minus k, that is q to the power 2n minus n, pq to the power n. And let us say we represent this quantity or this series by u2n. So u is the representation and this 2n says that we are considering this quantity after 2nth trial. Now what will be the value of u0? u0 value will always be equals to 1, because before first trial the particle rest at origin, that is r equals to 0. It means probability of particle at origin is fixed, that is equals to 1, because it is certain that before first trial particle will be at origin. So u0 will actually represent a probability, and u0 is representing the probability before the first trial particle is at origin, that is r equals to 0 or not. So definitely it will be there, so u0 will equals to 1. Correspondingly, if you expand this expression, you will get u2n as factorial 2n divided by factorial n to factorial n, pq to the power n. Now the numerator 2n factorial, if we segregate, the even multiplies with odd multiplies, and both is if divided by factorial n, because there is 2 times factorial n multiplied by pq to the power n. From this you can take two common. From this you can take 2 common, and if you take 2 common, you will get here 2 to the power or n times 2, and here you will get n times 2 also, that is automatically 4 to the power n. So by taking this 4 to the power n here, you actually get here 4 pq to the power n, and rest quantity can be proved easily in 4-5 step, that it will be minus 1 to the power n into combinatorial of minus half n. Now if we calculate the moment generating function of the sequence u to n, it will be equals to summation n equals to 0 to infinity u to n z to the power 2n, and this can also be calculated as 1 by under root 1 minus 4 pq z square. Just remember, small u to n represent the probability of the particle remains at origin or remains at r equals to 0 after 2nth trial, and uz, capital uz, represent the moment generating function of this sequence u to n. Now let us consider what will be actually meaning first return to 0. That was return to 0, but it was not there that whether after first trial it will return to 0, or first time when it will return to 0, or second time when it will return to 0. So let us try to calculate first return to 0. So first return to 0 occur at 2n if for all the cases s1 not equals to 0, s2 not equals to 0 up to s2n minus 1 not equals to 0, but s2n equals to 0. Only then we can say after 2nth interval the particle will return to origin first time, because if any previous value is 0, it automatically means that before 2nth trial the particle remains at 0. But since we want to calculate what will be the probability so that particle will return after 2nth trial to 0 first time, it means only s2n need to be 0, and before that none will be equals to 0. So this will be the event for which we actually want to calculate the probability. So let us say probability of this event Bn is represented by V2n. So this V2n will actually equals to probability S1 not equals to 0 up to S2n minus 1 not equals to 0, but S2n equals to 0. Automatically means this V2n comes out as 0. Now there are two possibilities in this particular case, that a visit to the origin is at stage 2n is either the first return with probability b2n, or first return occur at earlier stage 2k which is less than 2n with probability v2k, and thereafter it follows by an independent new return to 0 after 2n minus 2k stage with probability u2n minus 2k. Now maybe here it is little bit confusing, but if you consider u2n, u2n gives you the information that what is the probability that particle is at 0 after 2nth trial. V2n gives you the information that what is the probability that particle is at the origin after 2nth trial but first time. So we can write this u2n as a series of summation, that is u2n at a time may equals to v2n. This will represent, u2n represent what is the probability that particle will return to 0 after 2nth trial. So this may equals to particle is returning to 0 first time, that is v2n. This may equals to first time it is returning to 0 at 2n minus 2th trial. After that it is followed by u2 means after 2n minus 2, after 2 more trial, it will again return back to 0. Similarly, the third case will be v2n minus 4 into u4. v2n minus 4 means first time it will return back to 0 after 2n minus 4th trial, and thereafter it will, after 4th trial again it will return back to 0. So if we add up all these possibility, we are actually getting a summation v2k multiplied by u2n minus 2k, where k is ranging from 1 to n. So one more time, utn is the probability of the particle return to 0 after 2nth trial, means before that 2nth trial whether particle was reaches to origin at some, after some trial, it is not given, but v2n is the probability of return to 0 first time. So by using this v2n and u2s or uk's, we can determine u2n by this expression. Now we have just written this expression, and let us say we calculate the moment generating function of u2n now with u0 equals to 1. Again u0 equals to 1 because first time before the start of first trial, that is first trial is u1, but u0 will represent the 0th trial, means trial has not been started yet, and before trial the particle is at origin, so it is certain, that's why u0 equals to 1. So if we calculate moment generating function of u2n, it will be equals to uz, that will be equals to u0 plus 1 plus n equals to 1 to infinity u2n z to the power 2n. This is the formula of moment generating function we have discussed in one of the previous lectures. And if you substitute the expression of u2n, which is given by this series here, you will get this expression. And if you take the substitution n minus k equals to m in this, you will get this expression where m dependency and k dependencies are separated out, and this will be equals to uz, this will be equals to vz, that is moment generating function for u2m, that is uz, and this is moment generating function for v2m, that is vz. So uz will equals to 1 plus uz vz, and if you solve, you will get uz in terms of vz, that is 1 by 1 minus vz, and vz which will be equals to, by definition, n equals to 0 to infinity v2n z to the power 2n, that will be equals to 1 minus 1 by uz by this formula. uz we have already derived at 1 by 1 under root 1 minus 4 pq z square. So if you substitute here, you will get vz expression as this one. Now next we are going to calculate what will be the probability that particle will definitely return to 0 in a series of trial. Means there is the scenario that particle will never return to 0 if you observe it in a finite number of trials, but there is also probability that particle will return to 0. So we are going to calculate what is the probability that particle will definitely return to 0 after some trial. So this will be represented as particle will ever return to 0, that is ever return to 0 will be calculated as n equals to 0 to infinity of probability of the event vn, that is equals to n equals to 0 to infinity v2n, because v2n represent probability that particle will return to 0 first time after 2nth trial. So if we substitute here n equals to 0, means at 0 trial it will be at origin definitely. If you substitute 1 after 2th trial, it will be at origin, that will be the some value of v2, and similarly if you add up all these values, so you will get particle will return to, definitely return to 0 either after 0 trial, second trial, fourth trial, or all. then that will be equals to, if you see here, Vz is defined as 1 minus under root 1 minus 4pq z square, which is summation v2n z to the power 2n. Now here we are calculating summation v2n, means if in previous we substitute the value of z equals to 1, then you will get this quantity summation v to n will equals to v of 1 by substituting z equals to 1, and if you substitute z equals to 1 here, you will get 1 minus under root 1 minus 4pq. So just by those substitution, this quantity will result into v1, which is 1 minus under root 1 minus 4pq, and if you solve, you will get this as 1 minus magnitude of p minus q. This will be equals to 1 minus magnitude of p minus q, which will always be a quantity lesser than 1 for the cases probability of success is not equals to probability of failure. But if probability of success is equals to probability of failure, this quantity will always result into 1. What it means actually, if p not equals to q, then particle will return to 0 is 1 minus magnitude p minus q, means particle will never return to 0 will be 1 minus this probability, that is magnitude p minus q. So p represent probability of a success of a particular trial, q represent probability of a failure of a particular trial. So if we calculate magnitude p minus q, you will get that particle will never return to 0. But if p equals to q equals to half, you are getting the particle will definitely return to 0 as 1, means it is certain. What it means, if we able to maintain p equals to q equals to half, then particle will definitely return to 0. Now in later case, the v to n actually represent what is, because we have calculated particle will return to 0 by considering v to n, means we can say that v to n means particle will first time return to 0. So after 2nth trial, particle will first return to 0. That probability is 1. It means after 2nth trial, particle will definitely return to 0, or we can say that v to n represent the probability distribution for the waiting time for the first return to 0. It means after 2nth trial, particle will return to 0. So that 0th trial to 2nth trial will represent waiting time for the first return to 0, and the expected value of this random variable is just, you can get mu as b dash 1 by differentiating, and you will get this as 4pq by magnitude p minus q if p not equals to q, infinity if p equals to q. The proof is given in the literature, but we are not considering here. Now based on all this discussion, we can summarize or we can further understand this random walk model by considering this particular example. Let us consider that probability of success equals to probability of failure. It means both should equals to half. Under this scenario, we have just determined that probability that particle will return to 0 equals to 1. Now if we apply this logic in gambling, then we can say that in a fair game, that is probability of failure equals to probability of success with infinite sources on both sides. And this is also one meaning, that infinite number of resources are available on both sides. Probability of particle will return to 0 will equals to 1. And if we assume that if one bet in a gambling and if he earn, then that will be represented by some positive integer. If he lose, then that will be represented by some negative integer, and the value 0 means after some time he gains something but he loses something or same thing. So in total the return become equals to 0. So with this logic we can say that in a fair game, sooner or later one should be able to recover all the losses, since return to break even point is bound to happen. Probability that particle will return to 0 is equals to 1, means sooner or later this probability has to 1, and particle will return to 0 means if initially he has lost, then he is going to get recover all those losses. So after some trials he is going to recover all the losses. So you can say this is a optimistic approach for the person who is betting in the gambling, because he knows sooner or later I will recover all the losses. But the question is how long it will take to realize this break even point. That will be calculated by that mu value, that is 4pq by magnitude p minus q, p not equals to q, infinite p equals to q. What it means is, for fair game, when p equals to q, it will take infinite time to recover all the losses. What it means, the player will never recover his loss, let alone it realize a positive net gain. So this is the, we can say, a point which gambling houses actually prefer, because they know whoever is coming to play is going to lose, and this is the point which players normally prefer, because they consider they may lost in initially, but sooner or later they are going to at least recover all the losses. So this is just one practical example where we can use random walk. There is a further many other points also there in the random walk, which is actually employed mainly in gambling application, but it is also being utilized in stock exchange operation and many other that we have already discussed in previous slide. All the things that we have discussed here you can easily get in the value book Papolis, probability, random variable and stochastic process, and on this site. Thank you.